Good afternoon, everyone. Let's continue our chapter thermodynamics. Yesterday, was about different types of systems and variables. Now, we are going to discuss about zeroth law of thermodynamics. So, thermal equilibrium means two systems are said to be in thermal equilibrium with each other when only the temperatures are same. If they are at the same temperature, two systems are two. Look at it. Two systems are said to be in thermal equilibrium with each other if they are at the same temperature. If they have same temperature, then only they said to be in thermal equilibrium. So it leads to zeroth law of thermodynamics. So zeroth law leads to thermal equilibrium. Look at here. Any state of a system in which the thermodynamic coordinates remain unchanged. Thermodynamic coordinates remains unchanged is called state of thermal equilibrium. So here thermodynamic coordinates means temperature, heat, etc. State variables. Every equilibrium state of a thermodynamic system is completely described by specific values of some macroscopic variables like pressure, volume, temperature, and mass. These all are called as state variables or thermodynamic coordinates: pressure, volume, temperature, and mass. The relation among the state variables is called equation of state. Equation of state. For example, n moles of ideal gas equation is PV is equal to nRT. This is the equation of state of ideal gas. Here P indicates pressure, V volume, N number of moles, R constant, so T temperature. So here R is ideal gas constant. Next, ideal gas means it has to obey Boyle's law and Charles' law. Boyle's law and Charles' law. A gas which obeys Boyle's law and Charles' law is known as ideal gas. So equation of state of ideal gas is PV is equal to nRT. To state or to express equation of ideal gas, we used here pressure, volume, temperature, so number of moles. These are known as state variables or thermodynamic coordinates. Zeroth law of thermodynamics. Look at here. If two systems are at thermal equilibrium with the third system separately, two systems are thermal equilibrium with the third system separately, then the two systems are in thermal equilibrium with each other. Look at here. Here we took three systems: system A, system B, and system C. So A and B are connected with a diathermic wall with C. This is the diathermic or isothermal wall, which transfers heat from one system to another system. Here A and B are separated by a adiabatic wall, which doesn't allow heat through it. Means here no transaction of heat from system A to B. Look at here. No net exchange of heat energy because of A and B systems separated by a adiabatic wall. Adiabatic wall doesn't allow the heat through it. Means system A doesn't transfer heat to system B. Look at here. If two systems are in thermal equilibrium with the third system, means A and B are in thermal equilibrium with C, then the two systems are in thermal equilibrium with each other, then both A and B also in thermal equilibrium with each other. Diathermic wall, it is a conducting wall that allows flow of heat energy from one system to another system. This is diathermic wall. So it allows heat from one system to another system. Adiabatic wall. Here A and B are separated by a adiabatic wall. Adiabatic wall. This is adiabatic wall. So adiabatic wall, it is an insulating wall that does not allow flow of heat energy from one system to another. Means this wall, this adiabatic wall does not allow heat to transfer from A to B. Zeroth law. So if A or B are in equilibrium with C individually, then both A or B also in equilibrium state. This is the zeroth law of thermodynamics. Suppose, for example, suppose the temperature of system A is equal to the temperature of system C, because just before we assumed A and C are in thermally equilibrium, means the temperatures of A and B are equal, means the temperature of A is equal to temperature of C, means A and C are in thermal equilibrium. In addition to the temperature of the system B equal to the temperature of C, system C, means temperature of B is equal to temperature of C, because here A and B are in thermal equilibrium with each other separately with C, not each other. Now temperature of A is equal to temperature of C and temperature of B is equal to temperature of C. So from these two temperatures we can clearly say that temperature of A is equal to temperature of B, means A and B systems are also in thermally equilibrium. A and B are also in thermally equilibrium. So this is the zeroth law of thermodynamics. Zeroth law of thermodynamics leads to the concept of temperature. Temperature means the degree of hotness or coldness. The degree of hotness or coldness is called as temperature. The degree of hotness or coldness or the degree of heat is known as temperature. Thermometers work on the principle of zeroth law of thermodynamics. Thermometer works on the principle of zeroth law of thermodynamics. Temperature scales was designed on the basis of zeroth law of thermodynamics. Temperature scales means Fahrenheit scale, Celsius scale. So these scales were designed on the basis of 0th law of thermodynamics. Mathematical form of 0th law of thermodynamics is function of pressure and volume is constant. Function of pressure and volume is constant. Next, heat, work, and internal energy. First, heat. So, it is a form of energy which flows from higher temperature body to lower temperature body. It is the unknown nature which flows from higher temperature body to lower temperature body. Heat is the form of energy that transfers due to temperature difference between the system and surroundings. Heat always flow from the body at a higher temperature to a body at a lower temperature by itself. So, heat is the nature which flows from higher temperature body to lower temperature body. So, CGS units of heat, calorie. Calorie means the amount of heat required to rise the temperature of 1 gram of water from 14.5 degrees centigrade to 15.5 degrees centigrade at a pressure of 1 atmosphere is called standard calorie. 1 standard calorie is equal to 4.2 joules. So here we have to raise the temperature from 14.5 degrees centigrade to 15.5 degrees centigrade at 1 atmosphere pressure. So to rise temperature we have to give heat. That heat is known as 1 calorie. 1 calorie is equal to 4.2 joules. SI units, joules. CGS units, calorie. SI units, joule. The net flow of heat stops when the temperature gets equalized. The two bodies are then said to be in thermal equilibrium. So, to get thermally equilibrium state, temperature has to be equaled. Work. The energy that transferred from one system to another by the application of force at a point moving in its own direction is called work, or the dot product of force and displacement is known as work. Work is done by the system when heat energy is added to the system. Good here. Work is done by the system. Done by the system when heat energy is added to the system. dW is positive when work is done by the system. If we add the energy to the system, then work is positive. dW is negative, means work is negative when work is done by the system, done on the system. If work is done by the system, then work is positive. If work is done on the system, then work is negative. Heat and work in thermodynamics are not state variables. They are modes of energy transfer to a system resulting in change its internal energy. Internal energy. Look at here. Internal energy. We indicate internal energy with U. Internal energy of a thermodynamic system is the sum of the internal kinetic energy, internal kinetic energy due to molecular motion. Look at here, internal kinetic energy and internal potential energy due to molecular configuration of all particles in the system. Means U is equal EK, EK internal kinetic energy plus EP internal potential energy. So EK is occurs due to molecular motion. EK due to molecular motion. EP due to molecular configuration. The sum of EK and EP is known as internal energy. Next, the first law of thermodynamics. First law of thermodynamics. The fundamental principle involved in the first law of thermodynamics is law of conservation of energy. Law of conservation of energy means law of conservation of energy. Energy can neither be created nor be destroyed, but can only be transferred from one form to another. Energy can neither be created, means we cannot create the energy, nor be destroyed, we cannot destroy the energy. It changes its form one to another, but total energy will remains constant. It is known as law of conservation of energy. Statement of the first law of thermodynamics. The amount of heat supplied to a system, the amount of heat supplied to a system means Q or dQ is equal to the algebraic sum of increase in the thermal energy, increase in the internal energy and external work done by the system. Look at here. The amount of the heat supplied to a system is equal to the algebraic sum of, means total of, increase in the internal energy, means change in internal energy du, and external work done dw, means dq, the amount of heat dq is equal to algebraic sum of, means total of change in internal energy and external work done. So means dq is equal du plus dw. Here dq indicates the amount of heat supplied, du increase in the internal energy, and dw external work done. Look at here, dq is equal to du plus dw. Here dq indicates supplied heat, du indicates change in internal energy, and dw indicates external work. dq is equal to sum of du and dw. Between any two equilibrium states, the change in internal energy is equal to the difference of heat transferred into the system and work done by the system. So from this equation, we can write du is equal to dq minus dw, means change in internal energy is equal to difference between supplied heat and work done. So this is between any two equilibrium states, the change in internal energy is equal to, means du is equal to the difference of the heat transferred into the system and work done, means difference of the heat, means dq minus work done dw, means du is equal to dq minus dw. Here du indicates change in internal energy. dq supplied heat. dw external work done. Means du is equal to dq minus dw. Next, specific heats of an ideal gas. Specific heats. Specific heat means specific heat of substance is the amount of heat required to rise the temperature of unit mass of substance through 1 degree centigrade or 1 Kelvin. Means we have to raise the temperature of 1 unit mass through raise the temperature by 1 degree centigrade. To raise the temperature, we have to give the heat. That heat is known as specific heat. Specific heat of a substance is the amount of heat required to rise the temperature of unit mass. We have to raise the temperature of unit mass through 1 degree centigrade. We have to raise temperature through 1 degree centigrade or 1 Kelvin. So to raise temperature, we have to give heat. That heat is known as specific heat. C is equal 1 by m means unit mass. It indicates unit mass. dq by dt. So to raise the temperature 1 degree centigrade, we have to change the heat. That heat is known as specific heat. Means C is equal 1 by m dq by dt. dq by dt. To change or to raise the temperature, we have to change the heat. So this is specific heat. SI units: joule, Kelvin, joule, kg, Kelvin, joule, kg, Kelvin. So here joule is the units of heat, kg units of mass, and Kelvin is the units of temperature. So finally, the units of specific heat is joule by kg Kelvin. It depends on the nature of substance, its temperature, and the conditions under which heat is supplied. Means specific heat is depends on the nature of substance and its temperature and the condition under which heat is supplied. Look at here, M, Q, and T. Means C depends on nature of the substance, M, and temperature and heat. Next, variation of specific heat of water with temperature. So here we can discuss how the specific heat varies with temperature. Look at here. It was found that specific heat of water slightly changes with the temperature in the range of 0 degree centigrade to 100 degree centigrade, and specific heat of water decreases with increase in temperature from 0 degree centigrade to 30 degree centigrade. Look at here, from 0 degree centigrade to 30 degree centigrades, the specific heat will decreases. After the raising the temperature above 30 degrees centigrades, the specific heat value will increases. Look at here. Next, and increase from 30 degrees centigrade to 100 degrees centigrade. It leads the definition of standard calorie. Standard calorie: the amount of heat required to rise the temperature of 1 gram of water from 14.5 degrees centigrade to 15.5 degrees centigrade at a pressure of 1 atmosphere is called calorie. Means we have to rise the temperature of 1 gram water 14.5 degrees centigrades to 15.5 degrees centigrades at 1 atmospheric pressure. To raise the temperature, we have to supply some amount of heat. That heat is known as 1 calorie. So 1 calorie is equal to 4.2 joules. When heat is supplied to a gas, its volume and pressure change along with the change in temperature. When we heat any gas, the volume and pressure change along with the change in temperature. Next, specific heat at constant volume means at constant volume we have to rise the temperature 1 degree centigrade. It is defined as the amount of heat required to rise the temperature of 1 kg of gas, 1 gram of gas through 1 degree centigrade or 1 Kelvin when its volume is kept constant. Means at constant volume we have to rise the temperature of 1 gram gas 1 degree centigrade or 1 Kelvin. To rise the temperature, we have to supply certain amount of heat. That heat is known as specific heat at constant volume, because here we kept the volume as constant. So I wrote here specific heat at constant volume as CV. Here V indicates volume is constant. CV is equal to 1 by m dq by dt. Means here we have to remember volume is constant. CGS units, calorie by gram degree centigrade. SI units, joule by kg Kelvin. Next, specific heat at constant pressure means we have to rise the temperature 1 degree centigrade at constant pressure. To rise the temperature, we have to give some heat. That heat is known as specific heat at constant pressure. Look at here. It is defined as the amount of heat required to rise the temperature of 1 gram of gas through 1 degree centigrade, keeping its pressure constant. By keeping the pressure constant, we have to rise the temperature of 1 gram gas through 1 degree centigrade. For that, we have to give certain amount of heat. That heat is known as specific heat at constant pressure. So we indicate with Cp. Here P indicates constant pressure. Cp is equal to 1 by m dq by dt at constant pressure. Units same as CV, calorie by gram centigrade. CGS units. SI units, joule by kg Kelvin. Next, molar specific heat at constant volume. The amount of heat required to rise the temperature of 1 mole of gas through 1 Kelvin at constant volume is called molar specific heat at constant volume. Look at here. We have to rise the temperature of 1 mole of gas 1 mole means molar specific heat. To raise the temperature 1 Kelvin, we had to supply certain amount of heat. So that heat is known as molar specific heat at constant value. CV is equal 1 by N means unit molar or 1 molar. It indicates 1 molar. dQ by dt means specific heat. So specific heat for 1 mole gas which raises the temperature 1 Kelvin. Look at here. CV is equal 1 by N dQ by dt. Here N indicates number of moles. 1 by N means 1 mole. So to get 1 mole, we have to write small m by capital M. So from this equation, we can write CV is equal m dQ by small m dt. So dQ by dt. So in short form, we can write this as mCV. Here 1 by m dQ by dt is equal to CV. 1 by m dQ by dt is equal to CV, specific heat at constant value. So finally CV is equal mCV. Molar specific heat at constant pressure. Same. The amount of heat required to rise the temperature of 1 mole of gas through 1 Kelvin at a constant pressure is called molar specific heat at a constant pressure. So here we have to raise the temperature of 1 mole of gas by 1 Kelvin. For that, we have to supply certain amount of heat. That heat is known as molar specific heat at constant pressure. So in this process, we have to kept the pressure as constant. Cp means specific heat at constant pressure. Cp is equal 1 by N dQ by dt. Here 1 by N indicates 1 by N indicates 1 mole of gas. So for that, finally Cp is equal mCp. Here m indicates moles. Cp is greater than Cv. When gas is heated at constant pressure, the heat supplied to a system is used in two ways. They are to increase the internal energy of gas. Second one, to do external work, means dQ is equal to du plus Tw. So it is nothing but first law of thermodynamics. Look at here. When a gas is heated at constant pressure, means we supplied certain amount of heat dQ. That heat is divided into two ways. It increases the internal energy of the gas, means du, and do external work. dW means dQ is equal to du plus dW. When gas is heated at constant value, the external work done by system is zero. When gas is heated at constant value, then external work is zero, means we know dW is equal to PdV. dW is equal to PdV. So here we took volume as constant, means V is constant. So dV is equal to 0. Then dV is equal to 0. External work means dW is equal to PdV. Change in volume is 0. 0 into something 0. Then external work is 0. So that heat energy is used only for increasing the internal energy of the system. When we take as the volume, we take volume as constant, then total heat energy is used only for increasing the internal energy of the system, because external work done is 0. Therefore, at constant pressure, the amount of heat energy required to increase the temperature of 1 mole gas through 1 degree centigrade or 1 Kelvin is greater than the required heat energy at constant volume. Means Cp is greater than Cv. Cp is greater than Cv.
I conclude the session in 5 minutes.
Okay. So, from this lines, we can say Cp is greater than Cv. So, in next class, we can clearly discuss about isothermal process and adiabatic process and several types of processes. So, thank you.